Okay, let's continue the study pack 17, hydroxy compounds. In fact, we started this last week. Explained about the chemistry of the alcohols. We classified the alcohols as primary, secondary, and tertiary alcohols, and then we explained about the reactions of alcohols, the physical properties and the chemical properties. And the most important reaction being the oxidation of the alcohols, which is the primary alcohol and the secondary alcohols. I said the tertiary alcohols cannot be oxidized. The condition for the oxidation is that the OH attached carbon should be having at least one hydrogen attached to it. That's the reason why the primary alcohols and secondary alcohols can be oxidized, but the tertiary alcohols cannot be oxidized because the attached carbon has no hydrogen attached to it. And then we discuss about the products of the oxidation of the alcohols. The primary alcohols, upon complete oxidation, you get the carboxylic acid. When you add the potassium dichromate acidified with sulfuric acid, when you heat on the reflux, you get the carboxylic acid. But if you carry out partial oxidation for the primary alcohols, you get the aldehyde. That is by adding the oxidizing agent, and instead of refluxing, you heat and distill the product, right? And then we discuss about the oxidation of secondary alcohols. You get a ketone, right? And tertiary alcohols cannot be oxidized. There where we stopped in the previous lesson. That's question 10 on page 10. Let's continue from question 11 on page 10. Explain the reaction of carboxylic acids with alcohols to form esters. This is the esterification reaction. In fact, esters are sweet-smelling compounds which is formed as a result of the reaction between a carboxylic acid and alcohol. Let's see how a carboxylic acid can react with an alcohol to form an ester. This is a carboxylic acid, ethanoic acid, and the alcohol. Let's react with any alcohol you can react. I'm going to react with ethanol. This reaction is a reversible reaction where the forward reaction is catalyzed by concentrated sulfuric acid. And when you slide them, what happens is that a condensation reaction takes place. This alcohol, the oxygen, of course, the mechanism is not in the syllabus, but you should know why it's condensation. The lone pair on the oxygen attacks the plus carbon, right? It's addition followed by elimination of a water molecule. Addition followed by elimination of a water molecule. That's why, in short, we call this reaction as a condensation reaction. As you know, the condensation is given where addition is followed by elimination. That's a condensation reaction. So the product will be the ester, ethyl ethanoate, and plus water will be produced as a byproduct. This is ethyl ethanoate. I hope you remember how to name esters. When you're naming esters, first you name the alcohol part, ethanol. That means what comes next to oxygen is named first. This is ethyl. That is named first, and then you name the rest of it, ethanol, right? So ethyl ethanoate plus water is a byproduct. Now here, the most important thing is you need to know from which molecule gives oxygen to form water and which molecule gives the hydrogen. Here, the alcohol gives the hydrogen, not the acid. Generally, we know acid is a proton donor, but in this case, acid gives the OH and the alcohol gives the H. So if I'm to label these oxygen as O16 and the oxygen of the carboxylic acid as O18, the 16 oxygen will be ester and the O18 will the water, right? So that's how the oxygen, this is labeling of the oxygen atoms important because you need to know which atom gives what, right? Which molecule gives which atom. So the carboxylic acid, always the OH is given, and the alcohol gives the hydrogen, right? Clear? This is ester reaction. So you can likewise react any carboxylic acid with any alcohol to form these esters. Now, esters are sweet-smelling substances. They have a nice, sweet, fruity smell. They are usually used as flavoring agents, or in the manufacture of perfumes they use. This specific ester, ethyl ethanoate, has a pineapple flavor. Pineapple flavor, right? So likewise, any different types of flavors can be made using different alcohols and different carboxylic acids, right? And they are very important as the manufacturing of perfumes and flavors. You have flavors like, you have different types of essence like vanilla essence or strawberry or what you call it, banana. All these are artificial esters, right? What you get in the market as the food flavorings, they are all esters, and some of the esters, I would say most of it is highly, carcinogenic, cancer causing. Especially, it will have effect when you use it for long term. Especially these perfumes, it contains aromatic alcohols and carboxylic acid. Aromatic meaning molecules which has the aromatic compounds. We're talking about aromatic compounds in A2. Aromatic compounds are the compounds which contains the benzene ring. The benzene itself is a carcinogen. So aroma, the term aroma is used for the aromatic compounds because they have a nice smell, right? So aroma is smell. So therefore, if you use aromatic carboxylic acid or aromatic alcohols, the ester will be even, it will smell even better. But in that case, remember the benzene derivatives are carcinogenic, right? So this is the esterification reaction, and this ester which is formed can be broken down into the corresponding carboxylic acid and the alcohol by adding or using dilute sulfuric acid. So the form reaction is catalyzed by concentrated sulfuric acid, whereas breaking down of the ester, which is the backward reaction, is catalyzed by dilute sulfuric. Now, this is a reversible reaction, right? But if we want to increase the yield of the reaction, we can use acid chloride instead of a carboxylic acid. If acid chloride is used instead of carboxylic acid, you get a much greater yield. It won't be a reversible reaction. It will not be a reversible reaction, but the byproduct instead of water will be hydrogen chloride. And you can notice the same. The alcohol gives the H, and the other molecule in this case gives the chlorine. HCl is given off, and there is no catalyst used in this reaction because acid chlorides are highly reactive. So this is a forward reaction, and this gives a very high yield of the product ester. So you can use acid chloride instead of the carboxylic acid if you want to get a higher yield of the ester. Clear? This is a esterification reaction. So you need to know, especially if you're using carboxylic acid, who gives the OH, who gives the H, because sometimes, even if you remove the OH from the alcohol and H from the carboxylic, still you get the same ester, but there will be a problem if in the question, if the oxygen is labeled. The oxygen is labeled, the alcohol oxygen should remain the ester, and the oxygen of the carboxylic acid should be in water. Right? That's very important because this is addition followed by elimination. This is why we call this reaction as a condensation reaction. Right? Please copy these two reactions. This is question 11 on page number 10. Right. So that's the final reaction of the alcohols, the esterification reaction. Next, look into the most important reaction, which comes under hydroxy compounds. It is iodoform reaction. Now, this iodoform reaction is also referred to as the haloform reaction, because why we call this iodoform reaction as haloform is because iodine is a halogen. That's why we call it as iodoform reaction. This iodoform reaction is very important to identify the presence of the methyl carbonyl group in an organic compound. The methyl carbonyl group is this group, methyl group attached to carbonyl group. This is called the methyl carbonyl group, right? Methyl carbonyl group. It's an alkyl carbonyl group, but specifically it's only methyl carbonyl, not ethyl carbonyl, right? So we can identify the presence of methyl carbonyl group by this reaction, which is known as the iodoform reaction. So what we do is we simply add the iodoform mixture into this. Iodoform mixture being sodium hydroxide and iodine together. If your compound contains a methyl carbonyl group, iodoform mixture will react with this molecule and form the triiodomethane, which we call it as iodoform. Triiodomethane is an iodoform. It's basically it's a yellow precipitate, right? The antiseptic smell. I would say say a hospital smell, right? You get the into a hospital, you get this specific unique smell that's called the hospital smell. That is iodoform, right? That's iodoform. Triiodomethane. So this iodoform reaction is useful to show the presence of a methyl carbonyl group in a molecule. So you use sodium hydroxide and use iodine together. You slightly warm. If the molecule has a methyl carbonyl group, it produces a yellow precipitate iodoform, right? So let's see how the iodoform is produced stepwise. Actually, there are two steps which is taking place. One is known as a substitution step. The other step is referred to as the hydrolysis step. So I'm going to take a molecule which is a 2-one ketone which contains the iodoform. 2-one which contains a methyl carbonyl group. I'm going to add to this sodium hydroxide. Let me write it separately. Not enough space here, so let me write it here. This is the compound which contains the methyl carbonyl group. I'm going to add sodium hydroxide and iodine. Shortly, I'll explain why it's 3NaOH, 3I2. What happens here is that the presence of iodine, these three hydrogens, you can see the hydrogens attached to the methyl group, which is attached to the carbonyl. These three hydrogens are quite weak. The bond is quite weak because the carbonyl group is pulling electron. So carbonyl groups are electron withdrawing groups, right? We have discussed that before. Why? Because of the electronegative oxygen. Oxygen pulls electrons from the carbonyl group. Oxygen pulls electrons. As a result, this carbonyl group becomes electron withdrawing group. So that weakens this three carbon hydrogen bonds. So that results in the substitution of the 3 carbon hydrogen bonds with 3 iodines. This is what happens in the first stage. That's why we call this stage as the substitution stage. Right, that's the first step, right? Substitution, where the 3 hydrogens of the methyl group attached to the carbonyl is substituted with 3 iodine atoms. Now, why this 3NaOH here? Now, see, when the 3 iodines get substituted instead of the 3 hydrogens, there will be 3 hydrogens removed. Of these 3 hydrogens will be removed, and there will be 3 iodines remaining, right? Why 3 iodines remaining? Because overall we have 6 iodine atoms here. 3i2 means 6 iodine atoms. So out of the 6 iodine atoms, only 3 substituted here. So you have 3 iodines remaining. So remove 3 hydrogen atoms, and the remaining 3 iodine atoms will combine together to form 3 hydrogen iodide. It will combine to form 3 hydrogen iodide. This is acid. In fact, the strongest hydrogen halide acid is the hydroiodic acid. So this 3 acid to neutralize, we need 3 alkali. That's why we use 3 sodium hydroxide, because this acid which is produced should be neutralized, right? Because acid hydrolysis will take place if not in the next stage. We need to carry out the alkali hydrolysis in the next stage, right? So that's why we need to destroy the acid. So we add 3 NaOH, that results in 3 NaI and 3 H2O. So the byproduct which is produced in the first stage of the substitution, right, reaction is that you have 3 NaI and 3 H2O. That's the first stage of the iodoform reaction. 3 hydrogens attached to the methyl group in the methyl carbonyl methyl group will be substituted with 3 iodines. Why only these hydrogens, not any other hydrogen? Because these 3 hydrogens are attached closer to the carbonyl group, which is an electron withdrawing group. That weakens the carbon-hydrogen bond. As a result, the 3 hydrogens will be substituted with the 3 iodines. And then there'll be 3 hydrogens removed. We add in 3i2, there'll be 3 iodine atoms remaining. 3 hydrogens will react with 3 iodines to form 3Hi, 3 hydrogen iodide, which is acid, which will be neutralized with 3 NaOH, right, to produce acid alkali, salt water, 3 NaI, 3 H2O. That's the first stage of substitution. The next stage is hydrolysis. The hydrolysis, what happens, the 3 iodine atoms, in fact, this attached to the carbon, this carbon bond attached to 3 iodines and the carbonyl group, this bond get hydrolyzed. Now, what is hydrolysis? Now, hydrolysis is, hydro is water, breaking down is lysis. Breaking down of a substance using water is referred to as hydrolysis. Like we have electrolysis. What is electrolysis? Breaking down of a substance using electric current, right? So likewise, if you're breaking a bond using water, that's referred to as hydrolysis. The thing is, water itself does not have sufficient free H plus ions and OH minus ions. Therefore, hydrolysis cannot be achieved by water itself. Therefore, hydrolysis of 2 types. You have acid hydrolysis, that is when you have a little bit of acid, or you have the alkali hydrolysis, that is when you have alkali. So since we are already using sodium hydroxide here, we can carry out alkali hydrolysis. So what happens here? Look carefully. The 3 iodine atoms are electron withdrawing. These are electronegative, right? They are electronegative because we know halogens are electronegative. So they pull electrons because they have a greater effective nuclear attraction. So 3 iodines, but they're very weak compared to oxygen. Of course, oxygen is very strong. One of the most highly electronegative elements after fluorine is oxygen. So oxygen is pulling electrons. And the 3 iodines are also pulling electrons to itself because they are electronegative, right? So there are 2 electron withdrawing effects. Iodine is pulling on this direction. Oxygen is pulling electrons on that direction. So this is known as electron withdrawing. Right, so the bond, the carbon-carbon bond, as a result, get weakened. Right,